Hello guys, welcome back to my YouTube channel. This is third video of our series of nuclear physics. We are discussing the chapter nuclear structure and basic properties of the nuclei. The two properties, charge and mass, we have already discussed in the previous video. Here in this video, we will discuss the four other properties, size, density, nuclear spin or angular momentum of the nucleus, and fourth one will be the magnetic moment of the nucleus. So let us start with third property, that is size of nucleus. Atomic nuclei are considered to be spherical in shape because positive charge within the nucleus is uniform. So what shape has been considered for nuclei? It is spherical shape. And why this spherical shape has been considered? Because positive charge within the nucleus is uniform and uniform distribution of charge can be possible in spherical shape. On the basis of experiment, it was found that volume is directly proportional to number of nucleons. If R be the radius of nuclei, then what will be the volume of nuclei? 4 by 3 pi r cube. The number of nucleons are represented by mass number A. So 4 by 3 pi r cube is directly proportional to A. R cube is directly proportional to A. And R is directly proportional to A raised to power 1 by 3. R is equal to R naught A raised to power 1 by 3. Here, in place of proportionality sign, we have put equality sign and a proportionality constant R naught here. R naught is proportionality constant known as nucleus radius parameter, and value of this parameter is roughly constant for mass number less than 72. And the value of R naught is found to be nearly 1.3 into 10 to the power minus 15 meter or 1.3 Fermi meter. If we put the value of R naught in this formula, we will get the formula for radius will become R is equal to 1.3 A Fermi meter, 1.3 A raised to power 1 by 3 Fermi meter. To find the radius of light nucleus like carbon having mass number 12, we will put value of A here 12. And we will find that radius will become 3 Fermi for carbon nucleus and radius for uranium heavy nucleus having mass number 235. We will put 235 in place of A in this formula and we will get 7.2 Fermi will be the radius for uranium nucleus. The nuclear radius discussed above is the radius of nuclear mass distribution. Radius of nuclear mass distribution means radius of that sphere in which nuclear mass is distributed. There is one more radius, that is radius of nuclear charge distribution, means radius of that sphere in which nuclear charge is distributed. Since nuclear charge distribution also follows the same pattern as followed by nuclear mass. Because nuclear charge parameter is linearly proportional to mass number A. Since nuclear charge and mass number A both are linearly proportional, so nuclear charge distribution and nuclear mass distribution follow the same pattern. Or we can say that nuclear charge and nuclear mass both are distributed in the same sphere. Because sphere are same, so radius of nuclear charge distribution is equal to radius of nuclear mass distribution. The charge radius and mass radius both are the same thing. Let us move to the next property, that is density. The density of nucleus is found to be enormously high, of the order of 10 to the power 17 kilogram per meter cube. The order is 10 to the power 17, which is very high. So density of nucleus is very high. The density of nuclei of all the elements is very nearly the same. We can prove it from here. We will find the density of oxygen nucleus first, and then we will find the density of lead nucleus, and we will see that density will result in same in both the cases. So to find the density of nucleus of oxygen, what we require? Mass of oxygen nucleus and volume of oxygen nucleus. To find the volume of oxygen nucleus, we require radius of oxygen nucleus. So these two parameters are here. Mass of oxygen nucleus is 2.7 into 10 to the power minus 26 kilogram. Radius is 3 into 10 raised to power minus 15 meter. We will put this value of radius in formula of volume. So, then volume will be 4 by 3 pi 3 into 10 to the power minus 15 cube. If we put the value of mass and volume in the formula of density, so density of nucleus of oxygen will come 2.4 into 10 to the power 17 kilogram per meter cube. Similarly, density of lead can be found by putting the value of mass of lead nucleus and volume of lead nucleus in this formula. Mass of lead nucleus is 3.4 into 10 to the power minus 25 kilogram, and radius of lead nucleus is 7 into 10 to the power minus 15 meter. We will use this radius in the formula of volume, and volume will be 4 by 3 pi 7 into 10 to the power minus 15 cube. We will put this value mass and volume in this formula, and we will find that density of lead nucleus will result 2.4 into 10 to the power 17 kilogram per meter cube. We can see from here that density of nucleus of oxygen and density of nucleus of lead both are 2.4 into 10 to the power 17 kilogram per meter cube. Hence, both the nuclei have same density. Because of very high density of nucleus, it is said to behave like a compressible fluid. Because fluid state have moderate density. In compressible fluid means its density is very high. So because nucleus also have high density, so we can say that nucleus behaves like compressible fluid. Now let us move to the next property, that is nuclear spin or angular momentum of nuclei. The discovery of angular momentum of nucleus was the result of observation of hyperfine structure in spectra of elements. Foley in 1924 suggested that hyperfine structure was related to the properties of atomic nuclei. These properties are mass and angular momentum of the nuclei. Just like extra nuclear electrons, nucleons in the nucleus are in constant motion in discrete quantized orbit within the nucleus. Extra nuclear electrons means electrons which are revolving around the nucleus, and these electrons are revolving in discrete quantized orbit. Similarly, nucleons in the nucleus are in constant motion in discrete quantized orbit within the nucleus. Due to orbital motion, these particle possesses angular momentum and an associated orbital magnetic moment. These nucleons also possesses spin angular momentum due to spinning motion and an associated spin magnetic moment. So there are two types of angular momentum: orbital angular momentum and spin angular momentum. Therefore, total angular momentum I of single nucleon about a given direction is I vector is equal to PL vector plus PS vector. Sum of orbital angular momentum and spin angular momentum for single nucleon. PL and PS are the orbital and spin angular momentum of individual nucleon. So this is the equation for single nucleon. For nuclei containing many particles, resultant total angular momentum I is given by I is equal to L vector plus S vector. L vector is summation PL, it is total orbital angular momentum, and S vector is summation PS, this is total spin angular momentum. The total angular momentum I is usually called nuclear spin or intrinsic spin. So intrinsic spin has magnitude which is equal to under root I into I plus 1 into h cut, where h cut is h by 2 pi. I is total angular momentum quantum number, and that defines maximum possible component of I in any direction. Conventionally, we take z direction. So Iz max is equal to I into h cut. I is total angular momentum quantum number. So we can find total angular quantum number from this equation. If we have given Iz max maximum maximum Z component of I, then we can find the total angular momentum quantum number, and we will put the value of I in this formula to get the magnitude of total angular momentum, which is called intrinsic spin. The value of I depends on mass number A of the nucleus. If A is even, mass number is even, intrinsic spin has integral value, and for odd A, intrinsic spin has half integral value. Let us see how. Iz can also be written as Iz is equal to Lz plus Sz. Lz is sum of PLZ, Sz is sum of PSZ. What are PLZ and PSZ? PLZ is Z component of orbital angular momentum of single nucleon. And we have taken summation over all the nucleons to find the total orbital angular momentum. So PLZ is Z component of orbital angular momentum of single nucleon, and it is integral multiple of h cut for all the particles. And PSZ, it is Z component of spin angular momentum of single nucleon, and it is half integral multiple of h cut for all the particles. Yes, for even A, Lz and Sz, both are integral multiple of h cut, since Iz is integral multiple of h cut. But for odd A, Lz is integral multiple, while Sz is half integral multiple of h cut. Sz is half integral multiple of h cut. So Iz, which is total of Lz and Sz, will be half integral multiple of h cut. Thus we can say that for even A, Iz is integral multiple of h cut, and for odd A, Iz is half integral multiple of h cut. Let us move to the last property of this video, magnetic dipole moment. Magnetic dipole moment of nucleus is resultant of movement due to orbital motion and spin motion of the individual nucleons. Here one point to be noted is that neutrons do not have orbital magnetic moment. There are two types of magnetic moment, orbital magnetic moment and spin magnetic moment due to orbital and spin motion respectively. But proton has both type of magnetic moment, but neutron has only spin magnetic moment. So total magnetic moment, total magnetic dipole moment of nucleus is equal to summation over all the protons, orbital magnetic moment component and spin magnetic moment component for protons and spin magnetic component for neutrons. So this is mu PL is orbital magnetic moment for single proton, and mu PS is spin magnetic moment for single proton, and mu NS is spin magnetic moment of single neutron. Neutron does not have orbital magnetic moment, but they have spin magnetic moment, as I have already told. Although neutrons are neutral, yet they have spin magnetic moment. Neutron can be thought as containing equal number of positive and negative charge. Although neutron is neutral, but we can say that it is made up of positive and negative charges. When these charges are not distributed uniformly means at some position positive charge is more, at other position positive charge is less. So because of non-uniform distribution, we can say that neutron have overall some charge, very little but some charge. Then spin magnetic moment arises. This total magnetic dipole moment is called nuclear magnetic moment. This total magnetic dipole moment is called nuclear magnetic moment. The magnetic moment of nucleus is the result of interaction between orbital and spin magnetic moments. This magnetic moment is related to angular momentum vector I vector, and it is either parallel to or anti-parallel to vector I. How this is related to angular momentum vector? We can see from this equation, nuclear magnetic moment is equal to gamma I times I. We will put the value of gamma I here, that is Gi times E by 2mp. Gamma I is Gi times E by 2mp, which is gyromagnetic ratio. And Gi is nuclear G factor, and mp here is mass of proton. Magnitude of mu I is Gi E by 2mp into magnitude of total angular momentum. And total angular momentum, magnitude of total angular momentum is under root I into I plus 1 into h cut. So we will take h cut with this E h cut by 2mp, and we will replace E h cut by 2mp with mu n. Mu n is E h cut by 2mp, which is nuclear magneton. So value of nuclear magneton is E h cut by 2mp. We will put the value of E here and h cut in terms of electron volt, and 2 and mass of proton is 1.673 into 10 raised to the power minus 27 kilogram. So value of mu n will be equal to 3.14 into 10 raised to the power minus 8 electron volt per Tesla. Let us discuss how value of h cut can be found in terms of electron volt. Let us see here. We know that value of h cut is equal to h upon 2 pi. H is Planck's constant, and its value in joules is 6.6 into 10 raised to power minus 34 joule second. Joule second. To convert it into electron volt, we divide it by 1.6 into 10 raised to power minus 90. And 2 pi is also here. So we divide it by 2 and 3.14 again. So when we solve this, we will get the result will be 6.58 into 10 raised to power minus 16 electron volt second. So mu n will become 3.14 into 10 raised to power minus 18 electron volt per Tesla. If we do not divide it by 1.6 into 10 raised to power minus 19, then result will be in joule per Tesla, and it will be 5.05 into 10 raised to power minus 27, and joule per Tesla can be replaced with ampere meter square. So value of nuclear magneton will be equal to 5.05 into 10 raised to power minus 27 ampere meter square. And here in this formula, I is total angular momentum quantum number. Mu I z is equal to gamma I z max. If we take the z component, maximum value of z component of total angular momentum, then formula will become gamma times I z max. We will put here value of I z max, and I z max have value I into h cut. Maximum value of I z. We know that I z is mi times h cut, and mi takes value minus I2 plus I, and maximum value of mi is I. So I z max is I into h cut, and E h cut by 2mp is nuclear magneton. So we will replace it with nuclear magneton mu n. So formula will become mu I z is equal to Gi into mu n into I. We can remove this subscript z from here, and we can write it as mu I into gi. Mu I is equal to gi into mu n into 1. Why this z subscript can be removed? Because experimentally measured quantity is z component, maximum value of z component of total magnetic moment. We cannot find total magnetic moment, but we can find maximum value of z component of this total magnetic moment. It has been found that there is good agreement between the experimental and theoretical value of magnetic moments of various nuclei. Nuclear spin and magnetic moments of many nuclei have been measured, and important inferences have been drawn. Important inferences have been drawn regarding the structure of nucleus and other properties. This is the significance of nuclear spin and magnetic moment. We can, what is the significance? We can measure nuclear spin and magnetic moment, and important inference regarding the structure of nucleus and other properties can be drawn from these measurements. How? Let us see. For example, we have seen nuclear magnetic moment is far less than magnetic moment of an electron. Nuclear magnetic moment of one proton or nucleus is very less than magnetic moment of electron by the factor 1834, which is the ratio of mass of proton to the mass of electron. So because there is so much difference between the nuclear magnetic moment and magnetic moment of electron, so this fact indicates that electron cannot be present in the nucleus. So this inference regarding the structure of nucleus can be found. So this was about the significance of nuclear spin and magnetic moments. The remaining properties we will discuss in the next video. Thank you.